Greetings, students. Mr. Keister here again with you today. Today we're going to do Lab 12.1, study of the kinetics of reaction. In our last couple lessons, we've been talking about kinetics and reaction rates. And in our last lesson, we talked about rate laws. In this particular lab, we are going to determine the reaction orders and the rate law of a particular reaction. As I look behind me, had we been in school, this would have been happening on April 24th. Had we been in school, that's for Chem 2. If you're in honors, it would have been a few days after that. But as I've said many times before, those do nows are out the window, and we are now using our modified calendar and do nows document that's located on my Canvas homepage. So, without further ado, let me unfreeze the screen here, and we will look at our lab. So in this experiment, we'll study the kinetics of a chemical reaction. This reaction is called a clock reaction because of the means of observing the reaction rate. I think I mentioned this before in class, but the very first day of school back in August, we did a lab that actually involved reaction rates, and that was a clock reaction also. If you recall, we had two solutions, A and B, that were both either a little bit cloudy or mostly clear, and we poured them together, A and B, and then measured the time it took for the reaction to occur. And we were able to tell that because the color of the solutions when mixed together changed from, like I said, a clearish, cloudyish looking to a very dark purplish brown color. And that signified the end of the reaction. And so, and there was iodine located within the contents of that reaction as well. And iodine serves as the clock, as it will in this one too. So the reaction involves the iodination of acetone. So this is acetone, C3H6O. That is a common name that is used a lot. The actual correct name, organic name, is propanone, which is our smallest ketone. And so our reactants are acetone or propanone and iodine. And also we have a third reactant is actually HCl, which is the source of hydrogen ions that you see here. This reaction has to occur in acidic solution in order for it to happen. And so actually the hydrogen ion, which comes from the HCl, is also a reactant, and it is part of the rate law. This is the net ionic equation for that reaction. So our rate law is this: rate equals K, the constant, rate constant, times the concentration of acetone raised to some power, concentration of iodine raised to some power, and the concentration of hydrogen ion, which again comes from HCl, raised to some power. And those powers are, of course, the reaction orders for each of those three reactants. And we're going to measure each of those in the lab today. So the procedure is here. We're going to come to that, back to that in a few minutes. I want to go ahead and advance this up to the data table page. Okay. So this will give you a general idea of what we're doing today. We're going to run 5 separate experiments. And as you can see, here are our 3 reactants: 4 molar acetone, 1 molar HCl, 0.0050 molar iodine. And we have a 4th reactant here, water, which is not part of the rate law, but acts as a volume equalizer. And I'll explain that shortly. As you can see in experiment 1, we're going to take 5 mLs of acetone, 5 mLs of HCl, and 5 mLs of iodine. And to those 3, we're going to also add 10 mLs of water. If you add those up, we get 25 mLs total. In the second experiment, we are going to change the amount of acetone that we use. We're going up to 10 mLs. We're leaving these 2 the same. That should send off a bell in your mind, say, oh, I see now. Remember, when you're determining a reaction order for a particular reactant, you must keep the concentrations of the other reactants constant so that you can see that the change in the rate is due solely to the change in concentration of the one reactant that you're changing. As you can see here, between reactions 1 and 2, that's exactly what we've done with acetone. We're changing the amount of acetone while keeping the other two reactants constant. So anyway, 10 mLs acetone, 5 HCl, 5 iodine. Now that totals 20 mLs. And so this time we're only going to add 5 mLs of water, which gets us to that same volume total of 25 mLs. We've done the same thing in reactions 3 and 4. We have varied the concentrations of one of the reactants while keeping the other two the same. I should say varied the volumes of the two one of the reactants while keeping the other two volumes the same, and then use the appropriate amount of water to have the total volume be the same for all the experiments, which is 25 mLs. Reaction 5, same thing, 7.5 of each, only 2.5 mLs of water there to give us again our total of 25. So these are the volumes that we will measure out of each of the reactants for each of our experiments. Now, in data table 2, which is the important one, it talks about adjusted concentrations, all right? Adjusted concentrations. Here is why that says that, all right? So I already have some numbers written in here, and I want to explain where those come from. So let's look at this. So here we have 5 mLs of acetone, and that is just acetone, all right? There's acetone particles in there and nothing else. But when we add in the HCl, the iodine, and the water, the number of acetone particles remains the same, but the volume of the entire solution has gone up, all right? Which means that the concentration of the acetone has been diluted, all right? So think about that. Here's 5 mLs of acetone, it's all acetone, but now we got 25 mLs volume total, but still of that 25 mLs, only 5 mLs of it is acetone. And when you take 25 divided by 5, you get 5. We have diluted, excuse me, my eye's itching there. When we add the rest of our ingredients here, we have diluted the volume of acetone from 5 mLs to 25 mLs. So this is where the adjusted concentration comes in. All volumes that initially started at 5 mLs and ultimately ended up at 25 are being diluted by a factor of 5. And so right here, dilution factors for all 5 mLs will be diluted by a factor of 5. So now let's run down here and see how we use that. So our actual concentration of acetone was 4 molar, but that was with 5 mLs. When we diluted it to 25, if you take 4.0 molar and divide that by 5, you get a diluted concentration of 0.80 molar for that acetone. Same here with number 3. This was 5 mLs. That would be divided by 5 as well. So this one would also be 0.80 molar. And 5 mLs here, same thing. The 4 molar original divided by 5, 0.80 molar. And I can do that on the other two columns as well. Here it's already done for us here. So HCl started out at 1.0 molar, but when we go from 5 mLs to 25 total and divide that by a factor of 5, 1.0 divided by 5 gives us an adjusted concentration of 0.20 molar. And so as I look here in number 2, we also started with 5 mLs. So that would be also 0.20 molar, and that's it for that column. When we get to the iodine, iodine initially was 0.0050 molar. Again, we start with 5 mLs and dilute the whole thing to 25. We're again diluting by a factor of 5. So if you take 0.0050 and divide that by 5, we get the adjusted concentration of 0.0010 molar. We're going to do the same thing for the next two because it's the same initial volume and diluted by the same factor of 5. So those would also be 0.0010 mole. Now, here we have some tens, all right? So if you start out with 10 mLs initially at 4 molar, but we end up with a total volume of 25, now 25 divided by 10 is 2.5. So we have diluted now our original concentration by a factor of 2.5, and that will be true then of all of the initial concentrations that we ended up starting with 10 mLs and then diluting to the total of 25. So this one here, we would take our original concentration now and divide it by 2.5, which then gives us 1.6 molar here. These are all 2 sig figs, by the way, based on our concentration. Which makes sense. This is double this because we diluted this by half as much as we did the 5 ml ones. These two are also both 10, so we would take our 1.0 molar and divide by 2.5 for both of these. And so these then come out to be 0.40 molar. And then we have 110 over here in the iodine. And so that original concentration of 0.50 molar divided by 2.5 gives us 0.0020 molar. Okay. Again, water, we don't really care. Water is just the substance that brings the volumes equal for all the solutions, which is necessary to do. The last one, number 5, we have 7.5 mLs originally of actually all 3 of these. And if you take 25 divided by 7.5, you get 3.3 repeating. So our dilution factor for all the 7.5 ml ones is 3.3 repeating. So if we take the original concentration of acetone, 4.0, divided by 3.3 repeating, gives us an adjusted concentration of 1.2 molar. We take our 1.0 molar HCl and divide it by 3.3 repeating, the dilution factor. We get 0.30 molar. And then if we take our original concentration of iodine, 0.0050, divide that by 3.3 repeating, gives us an adjusted concentration of 0.0015 molar. Okay? Why did we need to do that? Because with determining a reaction order, all right, we use concentrations. We don't use volumes. All right? We use concentrations in determining reaction order. So it is necessary not only to use concentration rather than volume, but make sure we're using the correct concentration. Because like I said, even though this was 4 molar initially, that's just when you have acetone by itself. When you add all the other stuff to it, the amount of acetone is still the same, but the volume has gone up, which is going to cause your molarity to go down. Okay? All right, so this takes care of this portion. We're going to go back here in a second and talk about the procedure itself, and then we will come back and fill in the rest and then take a look at the calculations. Okay? It's 20. Okay, so now we're going to go back to the front page and take a look at the procedure now that we have all of our adjusted concentrations, as we mentioned just a bit ago, that we will use then in determining our rate law, in particular our reaction orders, and then ultimately our rate law. So as I go back here to the front page, of course we've got a lot of lines and numbers in there. Just kind of ignore those. You can look at your own paper. So we have our reactants here. Here's our 4 molar acetone and our 0.5 molar HCl, and or I should say our 1 molar HCl. Sorry about that. And then we have our water, and over here, of course, we have our iodine. So in the procedure 1, we're going to measure out 5 mLs of acetone, 5 mLs of HCl, 10 mLs of water, and finally 0.5 mLs of our iodine. The iodine must be added last because the iodine is the clock, all right? Just like we talked about in the reaction on day 1 back in August. The iodine acts as the clock, and so when the reaction has gone to completion, we will see a color change. In this case, our color will go from a light yellowish brownish color to clear. So let me go back then to the data table. And there we go. And so here we are, reaction 1, 5 acetone, 5 HCl, 10 water, and 5 iodine in that order. All right, so I'll put my goggles on here. And so I need 5 mLs of acetone. There we go. And then we will add 5 mLs of HCl. Okay. And then 10 mLs of water. Okay. Okay, I'm going to go ahead and add those in that order to our reaction beaker, or I should say our reaction flask here, Erlenmeyer flask. And then I'm going to need 5 mLs, yes, of iodine. Okay. Okay. I'm going to get this old stopwatch ready here. Okay. All right, so when I add the iodine, the clock will begin, and we'll see how long it takes for the reaction to go to completion. So, be nice to have a third hand here, but that's okay. Boom, boom. Okay. So, as you can see, and I'm swirling the flask, it is a very lightish, yellowish color, yellowish brown, but it's a very light. I want to see when this thing turns clear. Now, it's kind of tough to do that, so I'm going to kind of use a piece of white paper here to help. No, that helps a lot. So I can kind of look from the flask to the paper behind it and get a better idea of when we have gone clear. It's definitely lightening up some more. We are definitely getting close. I'm going to say we're there. All right. Definitely gone clear. Yep. Okay. For that time, I got 52.03 seconds. However, in this lab, we used class data. This is actually the class data from last year. This is one of those labs where the more data you have, the more accurate and precise it's going to be. And so we used the data from all 6 lab groups last year, combined it, added them up, divided by 6. And for that, it came out to be 49.98 seconds. And so that's the one we're going to go with. Mine was pretty close to that. Okay, I'm going to dump this out, rinse it out with distilled water, and now we will go on to reaction 2, which is now we're going to start with 10 mLs of acetone. Okay. Next, 5 mLs of HCl. Water, this time we just need 5 mLs. Okay. And iodine again this time is also 5. Okay. Again, I'm going to pour the first 3 in the order we discussed. Get the phone ready here. There we go. Clear. All right. Here we go. Going to add the iodine. Clock. Start the clock. Again, mine's a little delayed. Boom. And swirl the flask. Yeah, this one's going lighter, going more clear much more quickly. Boy, we're getting really close. I think we're there. Boom. Okay, I recorded 27.33 seconds. Again, using the class data from last year, that averaged out to 25.09 seconds. Okay, we will clean this out, rinse it out, and get ready to run reaction 3. So now I just need 5 mLs of acetone. Back to 5. Okay. 10 mLs of HCl this time. Okay. 5 water. Okay. And this time the iodine is again 5. Okay. All right. So again, I'll add the first 3 to our flask. Add it back on. Clear. All right. We're now going to get ready to run reaction 3. Again, I'm going to be a little delayed on my timer beginning because I'm missing that third hand. And there we go. Okay. Again, it's a very light yellowish brownish color, very, very faint. And again, it's starting to fade pretty quickly here. Once again, we are getting close, very close. The white paper really helps. We are about there. In fact, we are there. Okay, mine, I got about 28.57 seconds. Class data for last year averaged out to 27.55. I was only a second off. Not too bad. All right. So let me rinse this up. And we will get ready to run reaction 4. All right, so reaction 4, I need 5 mLs of acetone. Uh, 10 mLs this time of HCl again. There we go. Water, 5. 4. Oh, water is 0. Sorry, no water this time. And iodine is 10 this time. There we go. Okay, so I'll add these two. Again, no water on this one. Get the phone reset here. Okay. And here we go. All right. Now this one's a little bit more colorful. The yellowish brown color is more prevalent because, well, we used 10 mLs of it this time rather than 5 as we did before. So this has got more iodine comparatively. So my guess is it's going to take longer for this color to fade. Just guessing, of course. Okay. Yeah, it's definitely has slowed down from the last two. Finally, starting to lighten up now. Getting close. Getting really close now. In fact, I think we're there. Yep, we are. All right, so on that one, I actually got 58.11 seconds. The class average from last year was, let me see, 53.13. So there are our average class times. Now we're going to run down here. We're going to wait on number 5, as the instructions say here. And what we're going to do now is determine the rate of this reaction. Now I'm going to go back up here to the number 5 in our instructions. We calculate the reaction rate by dividing the concentration of iodine by the average time measured. Iodine is the clock, and so again, we're going to be utilizing its concentration as our benchmark for determining reaction rate. So then this would be, the rate would be the iodine concentration over T, all right? Yes, it's not really delta T, it's just T. All right, so for this first one, our iodine concentration is right here, 0.0010, and our time was 49.9 seconds. So for this first one here, we have 0.0010 molar over 49.98 seconds. And in rounding that to 2 sig figs, as our data is all in, we get 2.0 times 10 to the negative fifth molarity per second. Okay. Next one, same procedure. Iodine concentration 0.0010. The time here was 25.09 seconds. That works out to be the 2 sig figs 4.0 times 10 to the minus fifth molarity per second. And the other two would be done exactly the same way. You have the numbers. I'll let you go ahead and do that. Before we run reaction 5, we are going to be able to determine our rate law from reactions 1 through 4. So let's go to the next page, and I will get you started on that. So using the concentrations and reaction rates calculated in data table 2, determine the reaction order for each of our 3 reactants. Then determine the overall reaction order and write the rate law. I'm going to do the first one with you, all right? So the first one is acetone or propanone. And so remember, when determining a reaction order, we use our little equation here, C to the X power equals R. Where C is by what factor did the concentration change, R is by what factor did the rate change. So how do you do that? Well, we should know by now, to determine the reaction order for acetone, we have to choose 2 experiments whereby the concentrations of both HCl and I2, we have 3 reactants now, that both of those 2 are constant. And if you look back at your data table 2, that happens in experiments 1 and 2. In experiments 1 and 2, the concentration of acetone is changing and the other 2 remain constant. So if we look at those concentrations between experiments 1 and 2, we will see that the concentration of acetone doubled. That is 2 to the X power. And if you look at the rate column down in the lower data table between reactions 1 and 2, we just did that. Reaction 2 was 4.0 times 10 to the minus 5. Reaction 1 was 2.0 times 10 to the minus 5. The factor by which that is changed is also 2. So R is 2, X equals 1. So this is first order in acetone. Okay. You need to do the same thing for the other 2. You need to find 2 experiments whereby the HCl concentration is changing and the acetone and the iodine are not. And then same for the last one. You need to find 2 experiments where the iodine concentration is changing and the acetone and the HCl are not. Once you do that, you should be able to come up with a reaction order for each of these and then write the rate law for this reaction. Of course, we would add these orders up to get the overall reaction order and then write the rate law. Okay? Then, in number 2, it says using reaction 1's data, calculate the magnitude and unit of the rate constant K. So we're going to use reaction 1's data. I'm going to go ahead and write the rate law down here. Hopefully you will have calculated that on your own. This one, as we said, was first order. HCl also ended up being first order, and or hydrogen ion, which comes from the HCl, and the iodine was actually 0 order. So our rate law ended up being rate equals K times the acetone concentration times the HCl concentration, or the hydrogen ion concentration. The iodine was 0 order, so it does not go in the rate law. So using reaction 1's data, so you put the rate in here, which was 2.0 times 10 to the minus 5. You put in the concentrations of both acetone and HCl there, and you solve for K. All right, so that should give you a value of K. Remember 2 sig figs. And as far as the unit for K, remember that is determined by the overall reaction order. Since our overall reaction order is actually a second order, because this was first, and this was 0. Excuse me. That means that the unit for the rate constant K would have to be m to the minus 1, s to the minus 1, where those two exponents' absolute value adds up to the overall order, which is 2. And then down here at number 3, using the rate constant calculated above. So now you'll have a K, all right? Predict the reaction rate that you would expect in reaction 5, all right? So you're going to set up the rate law again. Now we have K. You're going to plug in the values of these two concentrations from reaction 5, and then you are going to calculate the rate, all right? You're going to calculate the rate. And that would be your theoretical rate. That would be your theoretical rate. Let's go back and do reaction 5 and get our actual rate. I'll just go ahead and plug these numbers in real quick. Just as a reminder, you should already have these down. Remember, this was the adjusted concentration of acetone there was 1.2 molar. HCl was 0.3 molar, 0.30 molar. And iodine was 0.0015 molar. So let's go ahead and do that and see what we get. So we're going to need 7.5 mLs now of acetone. There we go. 7.5 of HCl. There we go. Only 2.5 water. There we go. And 7.5 of iodine. There we go. Okay. Rinse this out real quick. Put in my first 3 reactants. Phone reset here. Okay. All right. Here we go. A little bit longer delay there. I'm getting slower. All right. And it's starting to fade. Not yet, but it's definitely getting lighter. Yep, getting close. Getting close. That's getting really close. I think we're there. Yeah, to set it down on the table on top of the white paper, you can really tell. Okay, that one, I got 32.22 seconds. Our class average, though, was 30 point, oops, that was up here, sorry, 30.81 seconds. up there for our average time in reaction 5. So calculating the rate based on that, we have our iodine concentration 0.0015 over our average time 30.81, and to 2 sig figs, that is 4.9 times 10 to the minus fifth molar. Okay, now that is our actual value for the rate in experiment 5. So as we go back to the calculations, and I'm going to let you finish these on your own. Remember, we calculated the theoretical rate from the data we have in reaction 5. We have our rate law. We have our value of K that we determined here. And so down here, our predicted rate then would be, or our theoretical rate would be plugging those numbers in for K and the concentrations of our two reactants in experiment 5 and calculating the rate. That'd be our theoretical. Our actual, we just said, is 4.9 times 10 to the minus fifth molar per second. And so from those two numbers, you are to then finish up and calculate your percent error. And I think you'll find that it is very, very close. So I think that finishes up Lab 12.1. I wanted you to see in real time how we go about determining a rate law. First of all, determining reaction orders first for each reactant, and then determining a rate law. From that, determining a rate constant value, and then being able to make a prediction by changing up the concentrations to whatever we want to, by making a prediction then of a rate based on those new concentrations. And like I said, as I hope you'll see, that the percent error came out very, very good. So that takes care of Lab 12.1. So until next time, everybody take care and stay safe, and I'll talk to you soon. Take care, everybody. See ya.